Hello everyone, and welcome to my presentation. I've had a wonderful time so far at this conference. So many great presentations that I could listen to. I really enjoyed it. I hope, so I have some plans to do some live coding. I hope I don't fail too miserably, but anyway. So my name is Roland Kuhn. I am leading the Akka project at Typesafe, and which many of you probably know. Thank you for that. And today I am talking about Akka HTTP. Akka HTTP is the thing that we have been working towards for quite some time now, many months. And we are getting really close to having that finished. Everyone, I think, is eagerly awaiting it. But for those who might not know enough about it, Akka HTTP is basically a port of the Spray project into Akka as a way to attach, to make the bridge between actors on one hand and HTTP, client and server, on the other hand. So to enable actors to speak HTTP. The Spray project has been, that came out of Akka, was then successfully developed by Matthias and Johannes, and now we are working together with them to reintegrate their successful development as, so to speak, Spray 2.0 into Akka as Akka HTTP. Now, it's called, or I say in air quotes, Spray 2.0 because we changed things. It was a very successful model, and we kept all the nice HTTP model that you will see. But the one fundamental change that we did is we lifted it from an actor-based I/O model onto streams. So this is why, well, the title says Akka HTTP. We will start out talking a bit about Akka Streams, which is the foundation on which this is built. So, with that preamble, let's switch on this thing, and then, oh yeah, the live demo. Now I thought we should just jump into it, just to see how it works and how it looks like. What you see here is I prepared some imports, I prepared some things so that I can demonstrate how streams work. Everything we do obviously uses actors, because Akka is based on the actor model, so we need an actor system before we can even start doing anything. Then we have a new thing called an actor flow materializer that we will need. And this is something that you will see in action very soon, that translates between the description of what a stream is and its actual execution, so we'll need one of those. We will make some ask pattern operations maybe later, so I created this timeout, and we might want to execute some futures. This is why I import the system dispatcher. So those are just preparations before we can get started. Now, if we want to just, let's say, print out a stream, first we need to create a source. So we say source, and there are lots of sources that we could choose from. Let's keep it real simple and say we start from a list of 3 elements. This is a source that will emit the numbers 1, 2, and 3 in this order, and then the stream is finished. So what we can do with this is we can say run for each print line, and if I compile this and run this and start this, you will see the 3 numbers have been printed. So far, so good. I mean, this should be fairly obvious. But what has happened here? It has actually done some work behind the scenes that you have that is nicely abstracted away, which also is the reason why it has taken us so long to write this project. So when you say source of something, that creates a description of this shall be a source. that does something. These three numbers are the simplest case. You could have one that does a TCP connection, or that does reads from a file, or does any other number of things. But the point is, this source is just a blueprint that describes what shall happen if you run it. It doesn't really run it. Then the run for each, what it actually does, this is a shortcut. What it actually does is it attaches a sync to this source that does for each print line. So far, so obvious. Scala collection syntax, if you use for each, put print line in, that is a description. Normally, but when you run that on a collection, it gets executed eagerly. But when I say this and run it, nothing happens. I mean, the console doesn't pop up because there is no output. The program is running, I should probably stop it now. It doesn't do anything, that's the point, unless you call .run on it. And that is a very important aspect of this. So now I added this and I run it and it runs. So this .run is where the magic happens. .run takes the description of I have this source and I have this sync, and it translates that into actors. In this case it will be two actors, one producing these elements, the other consuming the elements and printing them out. And in order to know how to do that, we have created this interface called Flow Materializer, and the implementation that I'm using here is the actor Flow Materializer, which will, as I said, turn things into actors. This is how a source gets executed, how a flow gets executed. Now what I can do is, instead of printing it out and using the source immediately, I could have assign it to something. So these are numbers. Numbers is a source of numbers, of integers. We could also have strings, just to have a different type to keep it a bit more interesting. So I have a source of A, B, and C. Now, if I have that, I should be able to compose. That is the second thing. We want these blueprint elements that we have to behave nicely so that you can plug them together and compose the functionality. So I want to create a new source from these two, which I would say is a composite one, maybe. So I also write source, but now instead of just having a simple constructor, I need to describe how this works. And this takes a constructor, a builder function. This B that we pass in here is a flow graph builder that will be used when we do things. So what could we do? Well, we have two lists, two sources of length 3. We could zip them together. Just a very simple use case. So first we need to somehow create a zipper. How does that work? Zip, I have ints and I have strings, so I write this down. This creates a zip. If you look at the type that this one is, oh, that's fancy. It doesn't say zip here. It says this, what we have created here, is a graph which has a certain shape. It's a fan-in shape. That's what we call it when something has more inputs and one output. That's a fan-in shape. So this graph is again one of these blueprint elements that we can use to construct our processing graphs. This is not something that I can directly use. You can imagine that this source and the block that we have here is just like opening a new white piece of paper, and now we start drawing on it. So in order to put this zip onto it, we kind of make a stamp. Now this is like a stamp, and we need to have it make its mark on the paper, which is called b.add. So we ask the flow graph builder to add this graph to this new blueprint. A source is something that has one output. It has no open inputs and it has one output. It generates things. So what we need to return from this block is that output. And what we can return here is zip.out. The important part here is, once you add a graph into one of these new blueprints, you go from graph fan-in shape to just the fan-in shape. And a fan-in shape is one that has certain input ports and one output port. The output port is zip.out, but now we need to wire up the input ports to feed the data into them. So for that we have a little graphical DSL. We can say numbers, and then we have this squiggly arrow, so they flow into zip.in0. And we have the strings, and they flow into zip.in1. This makes these two connections, so we take the numbers source, put it into this graph, wire it up. Now, this has created us a source. If you look at this, it says it's a source of pair, int, and string. So just to show that it works, we can run for each print line on this one. I should probably scroll this up, maybe. And of course, it prints the pairs. So far, so obvious? Okay. Now, these are just 3 elements. We could have done the same thing with strict collections. We can do something more interesting. We have now shown how we can construct things. There is one more aspect that I glossed over. I said we translate things to actors. Let's make a problematic case. Let's say we have a fast source. A very fast source can be constructed from an iterator, because this iterator is extremely fast. I should probably do something like this to be reminded that you all see it. So counting up from 0 takes nanoseconds. And if we run this source, it will be able to generate like a billion numbers per second. Now, if we want to run this via a map stage. So what I did not show yet is if you do the content assist on a source, you see all these methods that you are used to seeing from collections like drop and take, map filter, and so on. You see a few others there as well, because streams are more powerful. But let's just map. So let's map something, and this, artificially takes time. Let's say a second each. We don't change the element, we just make it slow. And then we run for each print line just to see what it does. So what happens is you see 1 number per second coming out. What you do not see is one CPU core constantly spinning. You would see it up here. The CPU usage is very low. So what you do not see is one core constantly spinning, executing that iterator as fast as possible. No, we back pressure that one. We can only consume 1 element per second, so we need to slow down that source, that fast source, to that tempo, to that velocity. And this, I think, is the main feature of Akka Streams, and it is also why we got into the Reactive Streams initiative to standardize how to do that thing on the JVM between multiple different frameworks. So how does this work? We have here, if you look at it, we have the fast source. Then we have the map stage, which takes a long time, and we have a consumer that should be pretty fast. And what we have a very smart guy who has studied some of these things and who came up with this idea. His name is Endre, and he came up with this idea of modeling the execution of this stream setup like a pinball game. So it was first called the pinball interpreter. What happens here is we have the print line stage, and that is ready to print something. So what it does is it has this this message token. It says it travels upwards here to the map stage, saying, I have capacity, I can print something, give me something. The map stage says, okay, I'll get you something, but I need data for that. I need a new X. So the pinball goes up to the fast source. The fast source says, oh, yeah, I give you a 0. Now, this source produces actually something. So it reflects the pinball that is now traveling downstream again. When it goes into the map stage, the pinball will be slowed down. It will sit there for 1 second, basically. And once that has elapsed, then it will be pushed downstream to the print line, which is the element to be printed out. And then the whole thing happens all over again. This is what is now called in the source the one-bounded interpreter, because there is only this one token that is just traveling upstream, downstream, upstream, downstream. If you have a filter stage, for example, data come in, and the filter condition is negative, the ball does not go on, the ball is reflected immediately, right? So you can have different kind of stages. You can even write your own. There's a whole DSL for that. So this is the magic sauce that makes this happen. Now, so far, this has all been very synchronous. We can also make this async. So this thread sleep is not nice. We don't really use that, we don't like that. So why don't we have something that's called map async? And it turns out that we do. So, instead of having a thread sleep for 1 second, we can schedule an event to happen in 1 second. There is the after pattern in Akka.Pattern, which can create a future after a certain timeout. Let's just say 1 second. We need a scheduler for that. And we need to provide the future. That would be future successful of X. So, after 1 second, only after 1 second the future is redeemed. The future is fulfilled. Sorry? If I run this, what will happen? Oops. What happens? So we note the numbers are printed in order. You might say they all wait 1 second, but there are jitter, I mean there could be race conditions. So believe me when I tell you, this operator makes sure that the numbers always come out in order. But why don't they come out 1 per second? This stage has the ability, the map async, has the ability to run things in parallel. And it does so by using the downstream demand that it got. So this is an asynchronous stage, actors talking with each other. So basically the print line tells the map async, you can give me not just 1 element, you can give me up to 4 elements. I am willing to buffer 4 elements for you. And then this map async will create 4 futures, and they can wait in parallel because this is all async and nothing is blocked. So how can we make this such that there is 1 element per second coming out? Well, we need to regulate the demand. And there we can do something. We create a flow element, a piece of the pipeline that will just have this property. So we don't have only sources and sinks, we also have flows. A flow is something with 1 input, 1 output. So we have a flow of int, and this one needs attributes. So we say with attributes, and there are a few attributes that we could set. One of them is input buffer. And if we set the input buffer size to 1, it should do exactly what we want. Now let me mark this out here like this. What we can then do, so we have this fast source and we have the map async from which we have created a source that does something later. And we have the sync over here, and we need to plug a piece of pipe that is pre-existing, that's this single thing, in here. For that there's the via combinator. So this will just insert this flow into the whole setup. So we are constructing the data flow pipeline from reusable pieces. Once again, And if we do this, then, well, it comes out one by the other, so with 1 second between them. So, everything clear so far?
If I wanted more, could I increase the buffer size?
Yes, so if you want more parallelism, you can increase the buffer size. This downstream demand, regulating it like that sounded like a good idea at the time. But we are actually changing it to be more explicit because there can be surprising behaviors. So in the next milestone, what you will see is that on the map async operation, you can explicitly say the parallelism that you allow for this operation. That's an API word. So streams are not final, they are not called 1.0 yet for exactly these reasons. We are ironing out the last few wrinkles and kinks in the API. So, what else can we do? What is interesting? We can make a TCP connection. TCP connections are interesting because we are going in that direction in this presentation as well. HTTP needs TCP connections. So what do? Well, we look for something that is called Stream TCP. Stream TCP is an Akka extension that will allow you to do streaming TCP operations. It has a few methods, and one of them is outgoing connection. So we need a remote address, the rest we can leave open, but where do we get the remote address? Yeah, maybe we should, before we can make a connection, we need something that listens. So we say bind. For bind, we need to create an address, eine socket address. Let's say I use localhost, and I don't know really where it's going to listen, and I'm too much used to Scala, so I forget the new keyword. So this will make the TCP extension bind to a random port on localhost. The question is, what does this return? That's the server. If we look at the type of this one, well, it's not actually a server of any kind, it just says it's a source of incoming connections. And that's really what the server socket is. If you materialize it, if you run it, then it will turn into something then that can give you incoming connections. So we need to actually run this. So the server needs to have an action that is executed. So we use the sync for each, and this one will get a connection. But the question is, what do we do with this connection? We can take a look what it has. Oh, the connection has a flow. So we use the flow. A connection is something that you can write to and that you can read from. So it has both a sync aspect and a source aspect. And a sync and a source is something that looks like it has one open input and one open output if you take it together. And that, well, is a flow. So this flow needs to be connected to something so that it runs. And for that, there is a join operator. A join can take two flows and join them together. You have this flow here and that flow there, and you just plug them together and then they run happily in a circle. What this flow gives you are byte strings. So we connect it with a flow byte string. And this will create this cyclic graph. You have this TCP connection and then you have just an empty flow of byte strings. It doesn't transform them, it doesn't do anything special, it just, whatever comes out of the source goes into the sync. Now we need of course to run it as well. Now we have a description of the server, and we should just run it, I think. So what do we get back from this? What is the type of type of this? It is a future of server binding. Where does that suddenly come from? Now, when you run just a source that is a list of 3 integers, I mean, it's quite obvious what it does. There is nothing else to it. But when you bind to a socket, especially if you bind to port 0, you somehow need to get the information out what the port was that was actually assigned. And you don't know that in advance because it's done by the operating system kernel. This is why all the graphs that you can materialize, all the blueprints, they have the data types that flow within them, but they have one more type, one extra type. That was the big change in the milestone 4 that we released recently, that we cleaned this up. This allows us to say a stream TCP server socket will materialize to a server binding, but we don't get it immediately because the bind may take time, so it's a future of server binding. So we have this future. Let's just print it out. For simplicity, I'm using synchronous calls here, so I await result. And let's see what this does. So it says it has bound to port 6061.2. So in order to make it a bit more fun, we need to connect to this port as well. So what we do is, well, there is a stream TCP outgoing connection, and the remote address is now known. Well, it would be if we were smart enough. Well, my address, well, it's not actually an address, but it's the server binding, but it's now in here. There's the local address that we can make a connection to. This will give us again a flow. You can view this as there's this sync where you can put in byte strings and they will go to the server. Whatever, then server sends something back, so you have again a source of byte strings. And from the client side, this looks very much just like a flow. It goes over the network and so on, but that's a detail. So this is the client. Now I could say I make a source. I make a source 0 to 10. So this just emits the numbers 0 to 10. I need to construct byte strings, so because otherwise I can't send them. I just make a hello X. I create some byte string with some content. And then, well, I send it via this client connection. And whatever comes back, I want to print out. So let's say we run it like this. What happens? Oh, yeah, I had the other one. So they are coming out as well. But you see, the byte strings come out. But, well, that doesn't look so nice. So this one should probably just be commented out so it doesn't disturb us. So for this one we can say map decode string UTF-8, right? So if you do that, then you see, so they come out in the right order, but it's not really deterministic which ones will be chunked together, because this goes over TCP connection and that is not message based. It's just a stream of octets, so they get lumped together in whatever way. Does that make sense so far? So we have the ability to speak TCP, and we do so using a streaming abstraction that can give us back pressure and that can be nicely formulated and composed. So that's what we have so far. With that, no, wait, there's one more thing I need to explain before I can go to HTTP, and that is, you don't always want to speak byte strings. Byte strings are really cool, but they are not always exactly what you want. Sometimes you have some sort of protocol that you need to be speaking, and I have prepared this here because live coding that would just take a bit too much time. Let's just say we have message, and we have two kinds of messages, ping and pong. And we have some simple functions one that transforms a message into a byte string and one that does the other. So it's a serializer and a deserializer. So we need to somehow put them into our streaming topology to run the things. So we say this is kind of like a codec, and a codec has two parts to it. It has one stream going towards the wire and one stream coming back from the wire. So it's a bidirectional flow. Bidirectional flows also have a constructor like this. And what we need here is we need to create two flows. So we say the top one is the one going towards the wire, is a flow that takes messages, and we map the to bytes function over it, and we probably want to import protocols. Exactly. So this is the top one, then the bottom one. We have incoming byte strings, and we have the function from bytes. And then what we need to do, well, a graph, as you've seen, as you might remember, a graph always has a shape, and that defines what it looks like to the outside. A graph is like, when you are done with this code block, a graph is like a black box that you close the lid on, but it has some holes in it, and that's what the shape describes. So there is a BD shape as well, and it can be constructed from, well, two flow shapes. These are flow graphs, so again we need to add them and like stamping them onto the new blueprint we do here. And then it should actually compile. Now we have this codec. We also have the problem that, so this codec emits byte strings of certain sizes, but if you want to parse them back again, they need to be cut at the right boundaries, so we need some sort of framing. And I've implemented that in here as well. So this is adding a length header, and then there is a frame parser. I think I'll share the code later that you can look. That's actually in the docs. It's in the upcoming milestone 5 docs. That's where it will be. So that you can look it up. The interesting part is, I said it should compose. It should you should be able to plug these together. So when we start out, well, we first want to do the codec, and then that's the top layer of our protocol stack, and below that we want to do the framing. And there's a top operator for that. So this is our protocol. Is codec a top framing, and if you look at that, that's a BD flow that takes messages into byte strings and byte strings back into messages. Now we can add this. We can use this protocol also when speaking over TCP. So what we can do is, on the client side, so while on the client side, we have this, now I deleted it, I could have, no, I could take a, yeah, to make it a bit quicker, no, so, let's just call this stack. So this is codec atop framing, and on the right hand side it should be the wire. So we join this to the client flow. This turns the whole stack into a flow from message back to message. So on the client side, we just go not via the naked TCP client, we go via this stack of protocols, which is the codec and the framing and the client. And we also, of course, need to not send byte strings, but we need to send pings. And we want to get back something from the server, which we need to add now. So the server, where did I put the server? Here. So here, the connection flow, that also now needs to have this protocol stack. So the server needs to do the protocols, just in the same way, but we write it now here from left to right. So the wire is on the left-hand side. So what we need to do is we have this protocol stack formulated such that the wire is on that side. So we need to, well, flip it around. So what we can do here is we can say join. I'll probably need to, otherwise it will probably not really work when I run it. I need to move this down here. So we take the, sorry. This is the joys of live coding. So take some planning, I think. So now we have the protocol dot, and it has a reversed operation. So we have the TCP, then we have the inverted protocol, so the server undoes what the client did, and then we join it with a function that now needs to deal in messages. So we could just have a flow message that uses the collect operator to turn a ping into a pong. So this compiles, but does it actually work? Let's see. No? What? What did I do wrong? Right. Client, where? Yeah. Yeah. Right. But there's something else wrong here. What did I do wrong? Join. Could it be that I need to say that this is a message? Oh yeah. So this is a word that I'll look into it afterwards. That must have been something, some covariance annotation missing. So what we've done is we created these pings, and we have this protocol stack, and we have the TCP connection, and we have the protocol stack on the server side, and we have the ping into pong function, and then it travels all the way back. And so now we see on the client the pongs 0 to 10. So with that, I think I should have explained enough about streams so that I can actually get to the HTTP part. And I'm running a bit late, but well, that's life. So the goals for streams, as you have seen, there should be no magic. You just write things down, and everything should be really composable. And we have an exhaustive model of stream processing. We have all the operators that I could not show you due to time. Consequences is we use these reusable stream blueprints, and we have this explicit materialization step that I couldn't really get into that much because I want to get to HTTP. Now, HTTP, well, it should be quite obvious why we want to add it, because Akka is about distribution, and there is basically, we have a solution for local, clusters of computers that are somehow, they need to be somewhat together and consistent, and for that we have Akka cluster based on Akka remote. But sometimes you want to have a more loosely coupled connection between a client and a service, and HTTP is the lingua franca for that. So this is why we are building it. And what I've shown you in the demo was exactly such a setup. This is how HTTP is structured. On the client side, we have it as a flow where you put in the requests in this case. They travel through the HTTP stack over the TCP connection. On the server, they are parsed into HTTP requests. Then you have some user application that does things. And in the end, well, you get back the responses in the same way. This is built, so Akka HTTP is built on Akka HTTP core. Akka HTTP core are the parsing and rendering stages that I just talked about. Akka HTTP itself is the routing DSL that you might know from Spray. And it's all built on Akka IO which in turn then uses the native sockets. So just to show you the pipeline layout, this is I think the main point of what fascinates me so about this way of building things using these reusable stream components. Because we have this TCP connection I've shown you is a flow. We have, well, not quite, we are so close. We have an SSL stage that is a BD flow. Then we have the HTTP server in this case, which is also a BD flow. And then the application logic is just a flow that transforms requests into responses. So the main point about the HTTP model is that Matthias and Johannes have gone to great lengths to make sure that it's properly typed and properly expressed. Everything in HTTP is modeled using immutable case classes, and everything has a proper name that is type checked by the compiler. We have no strings in there. That is, I think, the main benefit, main advantage of our HTTP model. It builds on the core and then adds this DSL, which has a nice properties, of which I want to show you a little bit. I hope I can make that work here. So this is something that we do not need to do. Nah. I'll just comment this out. So, what we want to do is we have a route, and there's this DSL for it. So I can just say path prefix demo, and it will match the path demo on this server. And then you have directives of all kinds. One of them can give you a directory listing from a browsable directory. So the users Kuhn comp demo HTTP, for example. I hope this exists. So this is a very, very simple path. Now we just need to run it. So what we do here is we say we don't use the stream TCP extension, we use the HTTP extension, where we say bind localhost port 8080, and then we run for each. We get an incoming connection, and for that one, well, we get this connection flow again, which we need to join to some flow. And the wonderful part here is a route. So this routing DSL describes nothing but a flow that turns requests into responses. So this should just work if we don't forget to run it. This was already run. So if I do this, I didn't print anything, I guess. I should have printed something. But if I go to the browser now and don't show all my private emails, then there was, what was it? Demo, which now serves this projects directory where you can click and surf around, and that's what this get from browsable directory does. There's a whole host of directives that you could use, but there's one thing I really wanted to show, and that is why have we based the project on streams. So let's do some upload. And the point is, if someone uploads something and you do something with it that takes time, you want to have proper back pressure handling, and that was something Spray was not really perfect at, because it needs the streaming abstraction. So we can extract the request object, and then we can say complete status codes OK, but before we do that, we say request.entity.databytes, and then we put them into a source, or we can, since I didn't really yeah, this should work. Sorry. Yeah, so this defines a flow for byte strings. So this is a source which we send via this flow to a sync.ignore. And then, I still didn't print anything out. But then, if we send a file, so using def0 here, oh sorry, this should be much larger, to upload, then it terminates immediately. I'm not running it. That's what I get. And now it's not running because I didn't terminate it. I'm sorry to keep you, but this is really the last point I wanted to make. So it's running again, trying to upload. And what you see here, so it transfers 2 megabytes because that's some buffer size, but then it doesn't because it's really back pressured on the server side by this very slow consumer that can just accept one chunk of whatever size it is per second. So sorry for being late, but so that concludes my presentation about Akka HTTP, and I'm open for any kind of question. Thank you. So when do I expect version 1 to be ready? For streams, we are very hopeful that we can get an RC1 out within the next 4 weeks. For HTTP, it will take a bit longer. It will take, we might decouple these two, because they are, I mean, one builds on the other, not the other way around. So for HTTP, it might take like 2 months before we reach that stage. But we'll keep you posted as we've done frequent development snapshots and you could follow it. How much do I expect that HTTP 2 will be a problem? Basically, that's the question. HTTP 2 has some interesting features that it will allow us to express also as streaming, because it has more freedom in the protocol itself, and we surely want to leverage that. I think our design is ready to handle that internally, but we have not yet started working on it because we need to support HTTP 1.1 first, obviously. So that is an effort that would probably only really begin in summer or later in the year. WebSockets. There is a pull request by Johannes Rudolph with an initial design for WebSockets. WebSockets will be in real soon, just like SSL. Yes? Sorry? Okay, so the long-term plan is to base play on top of HTTP core instead of Netty, because they do roughly the same thing. And Rich has written an experimental backend for play that is already based on the current snapshots of HTTP, so they are tracking our progress. You can expect that to, sorry? You can expect that to come out as soon as we are ready. I don't really, I can't speak for the play team, but all I've seen so far is they are closely tracking our progress. Yes?
Any plan to replace the active remoting netting implementation with this?
So, do we plan to base the Akka remoting on streams? Yes, we do. Simple answer. It will simplify the remoting layer quite a bit, and we're looking forward to that. So, thank you all for your attention.